Welcome to an in-depth look at a foundational skill in electrical work, conduit bending. It's an art, really, that demands precision and a solid grasp of some pretty specific techniques. Today we're diving into the nuances of hand-bending conduit, drawing our insights from a comprehensive guide on the subject.
That's right, Chloe. The core idea is that proper conduit bending and installation hinge on the electrician's skill, which comes from practice, knowledge, and training. This module specifically details methods for hand bending, covering everything from 90-degree bends to more complex offsets and saddle bends, and even how to prepare the conduit by cutting, reaming, and threading it.
So we're not just talking about casually bending a pipe. There's a lot of specific terminology here. Can you walk us through some of the key terms an electrician needs to know before they even pick up a bender?
Absolutely. For instance, a 90-degree bend simply changes the conduit's direction by 90 degrees. Then you have a back-to-back bend, which involves two 90-degree bends with a straight section in between. An offset is crucial for changing elevation, using two bends to go over or under obstructions, or for neat entry into electrical boxes. We also need to know about rise, or stub up, which is the vertical height of a bent section, and segment bends, which are large bends formed by multiple small bends or shots.
And stub up or rise, I see, refers to the vertical height of a bent section. But what about gain and developed length? They sound a bit more technical.
Developed length is the actual length of conduit that will be bent. Gain is a critical concept because conduit bends in a radius, not sharp right angles. The physical length of conduit needed for a bend won't equal the sum of the straight sections. Gain is the distance saved by that arc, especially in a 90-degree bend. Understanding gain helps prevent cutting your conduit too long. We also have concentric bends, which are 90-degree bends in parallel runs with increasing radii.
That makes sense. It sounds like there's a geometry lesson embedded in electrical work. Before we get to the actual bending, what are the primary tools for hand bending, and are there different types for different conduits?
Indeed, geometry is fundamental. For tools, hand benders are very common because they're portable and don't require power. They're designed to support the conduit's walls during the bend. These are typically used for smaller conduit sizes like 1/2 inch to 1 1/4 inch EMT or rigid conduit. A single hand bender can often bend both EMT and rigid conduit of corresponding sizes because their outside diameters are nearly equal.
So a hand bender supports the conduit. What about a hickey? The text mentions it shouldn't be confused with a hand bender and is used for RMC and IMC only.
That's a key distinction. A hickey functions very differently. When you use a hickey, you're not just forming the bend, but also dictating the radius. It offers very little support to the conduit walls, making it unsuitable for thinner materials like EMT. It's used for segment bends, where you make multiple small bends of about 10 degrees each until the larger bend is complete. You often see hickeys used for conduit stub-ups in concrete slabs.
And for PVC conduit, it's an entirely different process, right? You can't just cold bend it.
Correct. PVC requires a heating unit. You have to rotate the PVC evenly while it's in the heater, then remove it and bend it by hand. Some units are electric, others use liquid propane. Afterwards, a damp sponge helps it set faster. It's a very different approach from metal conduit. Also, remember that the bends must conform to NEC guidelines like Article 352 for PVC.
Let's get into the actual bending. The most basic, the 90-degree stub bend. What's the process for getting that right?
For a 90-degree stub bend, you need two measurements: the desired rise or stub-up height and the take-up distance of your bender. Manufacturers provide this take-up distance. You subtract the take-up from your desired rise, and that gives you the point on the conduit where your bend will begin. You mark that distance on the conduit, align it with the bender's starting mark, hold the bender handle perpendicular to the floor for leverage, and bend it in one smooth motion. It's important to use one foot to hold the conduit steady and keep your heel on the floor for balance.
one smooth motion. That sounds easier said than done. What happens if you overbend slightly?
The good news is you can usually use the bender to correct a slight overbend by bending the conduit back to the correct angle. However, the crucial part is knowing which side of the mark to place the bender, because placing it on the wrong side results in a gross error, as the guide puts it. After bending, you check the length of the stub up and verify the 90-degree angle with a square or level. If you overbend slightly, you can bend it back. Also, remember that a one-shot bend is what we just described, whereas a segment bend is formed by a series of small bends.
And this concept of gain you mentioned earlier, how does that factor into the overall length of the conduit?
Gain is the distance saved due to the bend's arc. Knowing the gain allows you to pre-cut, ream, and thread both ends of the conduit before bending, which saves time. The developed length of a bent piece is actually less than the sum of its horizontal and vertical distances when measured square to a corner. The difference is the gain. Manufacturers provide tables to help determine gain for different conduit sizes. We can also use formulas involving pi, 3.14, and the radius to calculate arc length for a quadrant, which is 1/4 of the circumference.
So it's about anticipating how the bend itself changes the overall dimensions. Let's move to something a bit more complex. Back-to-back 90-degree bends.
For back-to-back bends, you make the first 90-degree bend as usual. Then you measure the required distance between the bends from the back of that first bend. You reverse the bender on the conduit, aligning its back-to-back indicating mark with the measured point, and then complete the second bend. It's crucial to use outside measurements for accuracy.
Now, offset bends are something I imagine electricians encounter frequently given the need to navigate around obstacles.
They're incredibly common. An offset involves two equal bends, each less than 90 degrees, placed a specific distance apart. They're used to change elevation, to go over or under obstructions, or to properly enter boxes. The goal is to use the shallowest degree of bend possible because larger angles make it harder to pull wires through. It's a trade-off between space and wire pulling effort.
And there's a geometric component to offsets as well, specifically relating to right triangles.
Yes, an offset bend forms the hypotenuse of a right triangle. This is where trigonometry comes in. When you make an offset, some of the conduit's length shrinks or is used up. There are reference tables for calculating this shrinkage and the distance between bends based on the offset angle. These calculations derive from trigonometric functions like the cosecant of the offset angle. Understanding trig functions helps us calculate these distances.
It sounds like a lot of planning goes into this. What about parallel offsets, where you have multiple runs of conduit?
Parallel offsets are tricky because the bends are laid out along a common radius. You need to adjust the starting point of each successive bend so that the ends come out even. For example, if you're running two different-sized rigid conduit in parallel and need a 90-degree bend, you might put the smaller conduit in the larger shoe to ensure both bends have the same radius, though this trick only works for rigid conduit, not EMT, as EMT would flatten.
That's quite a detail. Moving on to saddle bends. These are also designed to go around obstructions. How do those work?
A saddle bend is used to clear an obstruction like a pipe. A standard saddle bend involves 3 bends, a center bend, usually 45 degrees, and 2 smaller 22.5-degree bends on either side. The key is to account for the shrinkage this bend causes. For every inch of saddle depth, the center of the saddle shortens by about 3/16 of an inch. You mark the center of the obstruction, then marks for the 2 outside bends, making sure to account for the total shrinkage when marking the center point A.
And there are 4 bend saddles, which sound even more complicated.
They are, because all 4 bends need to be aligned exactly on the same plane. A 4-bend saddle is essentially 2 offsets formed back to back. You determine the height of the offset, mark the conduit for the first offset, bend it, then mark and bend the second offset after the obstruction. Meticulous layout is required here. Practicing with number 10 or number 12 solid wire first can help anticipate problems.
It's clear that accuracy and planning are paramount in bending. But before bending, conduit often needs to be cut, reamed, and threaded. What's involved there?
That's the prep work. Conduit is cut to fit using a hacksaw or a pipe cutter. With a hacksaw, you need the right blade, 18, 24, or 32 teeth per inch, and a secure vise, making even strokes. Pipe cutters are quicker, but require careful tightening to avoid distorting the conduit. After cutting, reaming is critical. The inside edge of cut conduit is sharp and can damage wire insulation, so a reamer smooths that edge using a specific rotational motion, always wearing eye and hand protection. Finally, RMC and IMC often need to be threaded to join sections. This involves using a die head, either with a hand-operated ratchet threader or a power drive, and consistent lubrication with cutting oil. You must swab the oil afterward and inspect threads to ensure only one or two are exposed.
And I assume safety, like wearing goggles and gloves, is non-negotiable throughout all these steps.
Absolutely. Cutting, reaming, and threading all produce metal debris and sharp edges, so eye and hand protection are critical. For PVC, the solvents and cements used for joining are hazardous, so proper ventilation is a must when cementing, after wiping surfaces clean and dry.
This has been a really thorough look at conduit bending in preparation. The precision involved, the mix of geometry and practical skill, it's quite impressive. What's the biggest takeaway for someone considering this kind of work or just starting out?
The module emphasizes that sloppy or inaccurate bends lead to practical problems, like difficulty pulling wires, and can even violate electrical codes. The NEC allows up to 360 degrees of total bends between pull points, but making too many bends makes pulling wire hard, so planning is essential to minimize them. The Think About It sections throughout the guide highlight the importance of smooth, uniform bends and understanding concepts like gain and shrinkage. It really boils down to craftsmanship and attention to detail, like Timothy Ellie mentioned: hard work, respect, and an open mind.
That makes perfect sense. Thank you, LX1, for breaking down these complex procedures. The guide really highlights that hand-bending conduit isn't just a manual task, but a highly skilled one, demanding knowledge, patience, and a lot of practice. If you found this discussion valuable, please share this episode with someone who might also benefit from understanding the intricate world of conduit bending.